Okay, so we will today we'll talk about degenerate perturbation theory. But before I do that, let me just quickly once revise that what did we learn earlier. So we learned that if I have this problem and I know this solution, did I use N0? Yeah. How close I can go to this solution? So this was my full problem. Okay, this was my objective, and the board is clear, right? Is the board clear?
No, sir.
Okay. So how close I can go to this by making some systematic approximations, and we said that that is given by this. This is unperturbed plus epsilon sum over. So notice what is this?
The board is not clear.
Okay, you just said mostly, now then you said not clear. So what
Yes,
is the
sir.
reason? Is it the should we open that window curtain or something else?
It's actually blurry.
Oh, bloody. Bloody is probably a problem of focusing. Yeah. Okay, when he comes back, I'll tell him to increase the resolution and focus. But till then, let me write it down. Let me continue to write. So, then what are we trying to do basically? We are trying to, now technically what we are trying is something very simple. We are trying to express the solution of this full problem in terms of the eigenstates of the H naught, right? Eigenstate of H naught, and I can in principle always do that because H naught eigenstates form a complete set of states, right? So in principle I should be able to express this always. Okay? So this expression is given by the first term, the zeroth order term is just N naught, the first term is K naught. Can some of you go and get back him because this resolution seems to be still a problem. Yeah. Yeah, can you increase the ISO or the focus because the resolution is not clear? They are saying it's fuzzy. Yeah, the classroom have joined now. The online classroom. Yeah, they joined. Did they? No, they didn't join. They are out again. But they joined for some time. I mean, those students there in the classroom, they should know this number, whatever it is. Anyways, probably nobody is there. That's the reason. Yeah, can you see the board clearly now? Can you hear me?
Yes, sir. Now it's better.
Okay, so it's entirely a resolution problem. Okay, good. So what did we learn? That we wanted to express the full solution in terms of the solution of the H naught, and these coefficients are given by. So this is when I want to write. So n not equal to k. So this expression is basically H1. Let me write it as H1kn, and as we know this H1kn, this is basically a k naught H1 n naught. Okay. This divided by En naught by Ek naught. So this is basically this transition amplitude, order 1 transition amplitude, divided by the distance, the energy difference between them. Okay. Similarly, the second term is nothing but k not equal to n. Actually, I wrote k not equal to n and L not equal to n, and that is nothing but the probabilities of going from k to n. So two step. So n to l and l to k in two step. First n to l, all the possible ways you can go. So let's say you want to calculate from n to k. So this is some other level, and random levels are there in between. You can go from here to here directly in this term using one transition, or you can go from here to here via another step, which is your L naught. And this L naught is all the possible L naught, all the possible L naught that can be there. You sum over all of them, okay? And then the second transition is basically from this L naught to N naught, and then you will have this for each transition. You do this term, and En0 minus El0. Okay, this is the first term, and then there should be a second term. Okay, now you don't put the bracket here. I put the bracket here. The second term is the self term, where the k0 and n0 are basically same. So you can go do that also. H1 Nn, H1 Kn. Okay, all these possible terms. Similarly, there is a third order term and so on. So you can also think it that each of them are basically, in each step, you are basically expanding the order. Like this term is n1, first order, this whole term is second order. You are expanding each of this order in terms of the eigenstates of the original problem. So, or a more accurate way to say is that it is simply an expansion of the full problem, the full solution in terms of the eigenstates of the H naught. Okay, and you can in principle always do that because it's a complete set of states. Okay, and all you are trying to find is this coefficient. What is this coefficient of that expansion? Okay, so the other class is online now, right? Are you online? Can you hear me? The other classroom?
Hello, sir.
Yes.
Sir, here student not there, sir.
Oh, no students are there?
No.
Okay. But anyway, you keep that on because, yeah, so the class is officially on record happening. So now whether students are there or not. Okay. So today the class attendance is then 1, 2, 3, 4. 4 and 8. Okay, good. It's probably the first hangover, but I'm sure that hangover will be haunting you in NSEM. Okay, so if you don't come here, it's your problem. Okay, so yes. Sorry? Yes. What are you saying? I didn't follow. No, what do you mean by that? Yeah, so after this there are ordered epsilon q, right? And so on. Right? This is the order big O notation. So this is up to order epsilon square. Okay. Sorry? So yeah, sorry, what is the problem? H1?
Minus sigma k not equal to n k naught vector into h1 n.
Yeah, H1 NN.
So
Yeah.
going from
So this is you are going to K to N. Yeah, that's a point. Yeah, what should be the second term? K to L, L to N. So the second term is yeah, so this is basically, so this term when the L is N itself, okay, this is the same term when the N is L itself, right? So this is just that term. Okay, so this should not be picturized. Yeah, so you can picturize it as a, should we picture it as a return term? So N to L, L to N. Yeah, I think that would be more accurate. Okay, so this is something I need to check. Because this is not matching the picture. Yeah, I think I wrote something wrong here, or maybe there is a typo. The idea is this. So this term should be something like this. So this is going from N to L and coming from L to K. So which means it is going to a different level. But I want this term to be going from N to L and coming back. So I want this term to be N to L and L to N. Okay. So then this term will be En0 minus El0. Okay. En0 minus El0, and then this term should be just L not equal to L. Okay. So check that once. I think it's also wrongly written in my note, but check that. I might not be wrong also, but I think this is the term. So check the algebra and see if this term is that. Okay. So it's easier to remember it by picture, and the picture is this. This term is, you go wherever you can go by 2 steps. This is this term, and this is how many ways you can come back by 2 steps. Okay, this is second term. Second one is that, all the possible ways. So then it should be L0, okay, not K0. And this is a dummy index, so it can be anything. You can okay. I think that is what I did. Okay, nothing is wrong. So what I did is, this is a dummy index, right? So this is K, this is K, this is MK, this is KM. Yeah, the NN part is wrong, but this is what it should be. Right? This is a dummy index. I can always write it as K. Okay, I think that is the case. Good point. Okay, now there was one point of confusion.
We are eradicating the path where there's a loop like that, sir.
Sorry?
This is what it means. Like we're going from N to L, L to K, and we are eradicating the path where we're going like N to N.
I didn't follow. Say that again.
I mean, we are like eradicating the path we are going from N to N. That is what it means, sir.
How come you are getting this? This term is not there.
Minus sign.
The minus sign is different, but what you are saying, this term is not included here, right? This term is excluded. This is a separate term.
Yes, that's what are we like excluding that part from the N to N?
Yeah, you can say that. This is a special term which I am treating separately. Okay. If you want to picturize it physically, yes, you can say that. That as if I would have not excluding also, because this term is not there, so you cannot say that way. Excluding means this term is there and you are throwing it away. So you can say this term, you are separating that term and putting a minus sign to it. Okay? That is what is happening to that process. So all these processes are with a plus sign, except this process is with a pi phase. If this minus sign, you can also remember it as a pi phase, right? Okay, now there is one more small point I want to mention. Last time there was a controversy, there was a confusion that where I was saying that this n and n0, this c and epsilon, I wanted to take it as 1, but this problem is not there. So even if you take it as 1, that doesn't mean your perturbation is trivial. Right? And that confusion happened because you thought that both n and n0 are unit vector. They are not. Only n0 is unit vector. N is not unit vector. Okay? We normalize n at the end. So check this point, that if two vectors, their dot product is 1, that means they are parallel vectors only if they are unit vector. Right? If they are not unit vector, they are not parallel. And the simple way to check is that, let's do a simple example. This is Aij Bj cap, right? And let's say this is 1 by root 2, 1 by root 2j. So check that. So this is simply, this will give you a by root a plus b is equal to root 2. And there are many such vectors, right? This is not uniquely parallelly determined. Right? Only constant you have is a square plus, then later you put that constant, that a square plus b square is 1. Right? So everything I did yesterday still stands. There is no issue that I can put that c and epsilon and do that discussion, c epsilon, everything in terms of that. Okay, is that point is clear, right? To everyone? Okay. So with that clarification, so now that basically consolidates everything we learned so far. Okay. So now what I want to do, I want to show you that there, and then one more point I told you last time, that this n is not normalized, and that's why I am allowed to do all that, whatever I did. So what I did, what I said, that after the whole calculation is over, you calculated the n up to a certain order in epsilon, then at the end you calculate this, and that for that you find a factor that does this job, such that when you sandwich them, then this Zn square is identity, okay, up to that epsilon order. And we find also how to calculate that we discussed last time extensively. So I will not rewrite that expression again, but okay, let me write just the expression. So this Zn, we calculated this to be up to order epsilon square is so this is basically the leakage probability, which means if there is no overlap between k and n via h1, then this term will be 0. But this one, because of that overlap, this term is this term will be 1, and then you are getting something different from 1. Okay, so this was basically everything we discussed so far about the perturbation theory, and today we will try to see there is an issue in this whole program when there is a degeneracy, and that is kind of obvious that there is an issue because there are this kind of terms everywhere. If these terms are going to 0 because of degeneracy, we will start seeing some problem. Okay, so let's try to address that point. Okay, let me write in this part. So up to what extent I can write? So let me write it here. Okay. Okay, let's now talk about the issue with degeneracy. Degenerate toy model. Let's do a toy model and try to see the problem. Okay. So let us say my H naught is this. So how many students are there in the online classroom now? Is there anybody? I wonder how wild was the feast. That it is now 2 p.m., right? Yeah, anybody is there?
Yes, sir.
Oh, how many people are there?
One.
So I wonder that it is 2 p.m., right? People are still couldn't able to lift themselves and come to the classroom. So I wonder what happened yesterday. Okay, so H naught is so this is my H naught, and I want to deal with the H1, which is 0, 1, 1, 0. Very simple, because H naught is already diagonal. and h1 is just something that is making it off diagonal, right? And this problem, if I write it as a epsilon, so h is h naught plus epsilon h1, then the full problem is basically 1 epsilon epsilon 1, and eigenvalues are basically 1 plus epsilon 1 minus epsilon, and the eigenvectors are for this 1 1 1 by root 2 1 minus 1. And this one is also trivial. This one, the eigenvalues are 1 and 1 degenerate, and eigenvectors are 1 0 0 1 or any combination of them, right? Because they are degenerate. So this is the problem. Let us say I want to solve it using this formula, right? We all derive this formula, and let's see what happens. Okay. So this is my E1 0, this is my E2 0, and this is my 1 0, this is my 2 0. Okay. So okay, one more point I forgot to mention here. So this is how the states are there, and of course you want another quantity which is delta n, and delta n at a particular order k will be given by n naught delta n to the power k minus 1, or k minus 1th order. So if you want it at so delta n is basically delta n at order k is En at kth order minus En0. Okay. So if you want to calculate this at a particular order, you have to know the state at one lower order, which you of course know because you at the beginning you know the states at 0th order, both of them, and then you gradually build up from this, right? So you know everything you need to know about the problem up to order epsilon, right? So we are going to use this formula and see where we can get. So this is the actual solution. Okay, and now we are trying to see what can we do by perturbation. Okay, so the perturbation will give me En order epsilon and this term up to order epsilon. So for E1 epsilon it is E1 0 plus epsilon H1 1 1, which is 1 plus epsilon 0, that is 1 again, right? And that you can calculate because H1 1 1 is basically 1 0 H1 1 0.
Excuse me, sir.
Yes.
So the board is not visible for us.
Okay. What is the problem?
It's very dim.
Is resolution or something else?
I think it's the light.
Okay, light. So can you try to curtain down and see what happens? We are just going back and forth on this curtain. Okay, so this quantity I can simply calculate. 1 0 is basically this, and H1 is basically 0 1 1 0, and this is 1 0. This is nothing but 0. Okay. So that's why I am putting that term to be 0. Is it clear now?
No, sir.
Okay, so what's the resolution of this? Is it light?
Can you turn on the light?
Okay. So, yeah, can you turn that on? Yeah, how about now? Turn on that one also if you have. Yeah, how about now? It's probably too much.
So no, sir, the second one is too bright.
Second, okay, turn that off. No, that, yeah, and now turn, yeah, now, how about it? How is it now?
So the light is better, but now the resolution is low.
Okay. Okay, can you call again that guy? Hey, this perpetual problem is very difficult to pass to finish a course like this. Problematic to see in projector, okay.
Sir, I am attending from laptop and from it is fine.
Okay, so it's a projector problem. Yeah, so then I think it is better to attend from your laptop or whatever at your respective places or even in the classroom. Maybe you can keep the listen it in the screen and watch it from. It's a so yeah, it's a projector is probably the problem. Okay, let me write down the next equation also. Yeah, let's wait for him. Yeah, so they are saying the resolution is not clear. Can you see what's the problem? Did you increase the ISO?
Yes, sir.
Yeah, so I don't know why it is a. So if it is a problem that it is not visible in the screen, then you can try using your laptop. Oh, now it looks better. How is it now? Can you respond online classroom? It's good. Can you say that again? What did you say?
Sir, it was better before.
Okay, so
very
they are
dark.
saying, yeah, so it's probably the light and brightness setting. Okay, then. Okay, so let me discuss this point. I just wrote down it. So you can see there are two problems already happened here. That first problem is I calculated the first order correction, the first order corrected term, and I found there is no correction, right? It's just one. And that's clearly wrong because I know there is a first order term, right, in the actual expression. And second thing I found, I cannot actually execute this calculation because this term is going to blow up every time, right? This En0 minus Ek0 because there are only two levels and they have the same energy. Okay. So these are the two issues. That one thing is the first order expansion is failing, and the second thing is this. Now let's try to go a little deeper that why this issue is happening. Okay. So one thing is to notice that the eigenvectors of H0 are itself a bit ambiguous, right? Because let's say there are infinitely many choices of linear combination which are the correct eigenvectors, right? So here one thing you want from your perturbation theory that when you take your epsilon to 0, right, you will fall back on the problem of H0, right? And that is, there is no guarantee for that to happen because you don't know which H0 you started with. You have not fixed yet, your H0 needs to be fixed properly, right? So these are the two problems we would like to deal with. Yeah. Yeah, you know that it's a degenerate thing, right? So degenerate means there are infinitely many combinations of eigenvectors which are also eigenvectors, right? So this choice, this is a choice that I made. There are infinitely many such choices, right? I can write a C1 plus C2, that is also an eigenvector, right? So my problem is, even if I start with a combination, so let's say I select a particular combination at the perturbation, and then I take the epsilon to 0, then I can go back to any of this, right? Need not be the one I started with, right? So this is one problem. So we must choose, first thing is we must choose the basis, the correct basis where we fall back when the epsilon goes to 0. And second thing, we must avoid this kind of divergences. These are the two technical problems, and of course it is giving me wrong result to begin with. Right? So let's see how to fix this. And so we identified the cause of the problem. The cause of the problem is your H naught eigenstates are itself ambiguous, right? Because there are infinitely many choice of eigenstates. So let's see how do I fix this problem. So let me write down once more time the problems. So the problems okay. So the first problem is when I write this thing which is some Cnk k0 k, right? This is the expansion I'm trying to do. Right? This is and these terms as En0 minus Ek0 in denominator. Right? So they are blowing up. They are going to 0 because of degeneracy. Right? This is the first problem. The second problem is ambiguity in k naught. Okay. So there are infinitely many possible k naughts. I am just starting with one of them. Then I am turning on my perturbation, and then when I am turning it off, there is no guarantee that I will come back to what I started with. Right? So this is going to be a problem. Okay. So we want to fix these two issues. We have to do something to fix these two issues. Okay, so the fixing of these issues is very similar to the issues we faced in simultaneous diagonalization problem. If you remember, there was the same problem that we don't know how to fix this eigen basis to something. We did something to fix the eigen basis, that is common eigen basis of two commuting operators, in which one of them is degenerate. So let me state the problem once more before I discuss a possible solution. Okay. So now I generalize the problem. So let's generalize it. So let's say I have a H. So I discussed everything for a simple example. Now let's generalize it. And this H naught is degenerate. I will do it in two steps. First I will say it is degenerate only in ground state. Later I will do this when it is generally degenerate at any state, anywhere. Okay. So let us say my states are like that. There are two states. One is E10 for this H naught, and there is EQ plus 10. So this is Q fold degenerate. There are Q states which have exactly same energy E10. Right? And the Q plus 1x is the next one, which is not degenerate. And we assume generally it is true, although it is not always true, that as I turn on a perturbation, so this is my epsilon, it goes from 0 to 1 and take me to H, then this degeneracy is lifted. Then there are Q levels. Degeneracy is lifted and they are E11, E21, EQ1. So this is okay. This is 0 because here I am saying I have not done anything, right? Or maybe let me write more accurately. This is also 1. Okay. So after the perturbation is lifted, the degeneracy is gone. This is not always true because see think that why degeneracy is there. Degeneracy is there because there was some symmetry in the H naught, right? So generally you are talking about a general form of perturbation which breaks that symmetry. Then the degeneracy is gone, and that was the case in the problem that I have discussed just now, right? This 1 degeneracy was broken to 1 plus epsilon to 1 minus epsilon because this new Hamiltonian doesn't have that symmetry which was there in the origin. This is not always the case, and that we will discuss separately. Maybe the perturbation is such that it is also has some symmetry, then all the degeneracies will not be lifted. Okay? Although it is unlikely or most likely that will never happen, but one can think of tricky situation where that might happen, that the original problem doesn't have a symmetry, but the perturbation turned on that makes it symmetric. That is very unlikely to happen unless the perturbation is cancelling some term in the original Hamiltonian. Right? So then that scenario we will not discuss. So it is not. It will be never like that. That the original problem has no degeneracy, but the part-up problem has degeneracy. Right? So we will not discuss that kind of scenario here, although that is not theoretically ruled out. Okay. So basically, our goal is to calculate this. How do I calculate this? And we have seen that this is not going to work because I don't know these corrections because of these things blowing up. So I cannot calculate this delta n's because delta n requires me to calculate, for example. Right? I don't know this because of this blow up. Right? So let's see how do I fix this. It's a very simple strategy. And as I told you that if I proceed by the non-degenerate perturbation theory formula, these denominators will blow up, and basically the idea is this: if I go by the non-degenerate perturbation formula, my first order corrections is, for example, so let me call this thing C and K. So I had the degeneracy. So that means E1, should I write it? Okay, I'm mixing up some notation here. Oh no, it's fine. So this 0 means it's 0th order. E2 0, E3 0, EQ 0. They are all equal. Okay. So for all this term, this denominator will be blowing up. So C and K doesn't exist for n k less equal to q. Okay. So what do I want? I want to construct. So our goal is to construct a new set of basic function, a new set of n naught that diagonalize H1 Kn, this matrix. Okay. And what happens if it diagonalizes that? That means in this new set of basis function, this term will be 0, right? And if this term will be 0, those processes will be forbidden, right? And if those processes are forbidden, then this term will not even feature in this summation. Okay. So this is the way to fix the problem. So this is doesn't exist. For them it become C and K will become 0. Okay. Okay. So this is the outline of the scheme. Okay. And so then how does the solution will look like? So basically the outline is, let me write it here. So this much, knowing this much is actually enough to solve all the problems that generally arise in the coursework. But I will go a little more rigorous than this and prove it for a general case, or show it for a general case instead of showing it. Right now we are doing everything for ground state, only for the lowest state. But it can be so this degeneracy is somewhere in the middle. Right? Then it becomes a little tricky. Right now it is very easy. Then it is also very easy. Then you have to just identify that block, that particular degenerate block. So your job is diagonalize the Q by Q submatrix, which is basically that K naught H N naught. This, which is between these Q states, So diagonalize this Q by Q submatrix. A diagonalization means you are moving to a new basis in that space, which is A N K K naught, K equal to 1 to Q, right? You are moving to a new basis for that subspace, right? and then you calculate n h1k, and that will be delta nk h1 nk, whatever it is, where n and k both are less than q. Okay. So now your full basis will be this nk. So 1, 2, q, right? Instead of 1 naught, 2 naught, q naught, plus whatever else. This is your new basis, and you work here in this new basis. Okay. So this is the strategy. Everybody got this point? Is it clear? So picturize this. So let me picturize this in this part. So the outline is very simple. It should be forever etched into your memory once you see this. There is not much to do. So you write. So you see where the problem came from. The problem came from in first order because this term was blowing up because of the denominator. So you want to forbid this process. This term doesn't exist, right? Then it will go to 0, right? So the blow up problem will go away. So what to do? You construct the H1 matrix. What is this? This is the full. This is the H1 matrix. Full H1 matrix. So what is the full H1 matrix? That matrix is H1 1 1 H1 1 2 like that. Yes. Only H1.
That's like H1, right? Not H. The diagnosing H1.
No, only H1. I'll tell you why. The problem is those states. What? Oh yeah. You are correct. This H1 only. Okay. Okay. So this is H1 dot 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 1q. Right? So H21 dot dot HQ1, right? HQQ. So this is the problematic part, right? And then there is the rest. The rest of the terms are also there, right? Okay. But the rest of the term I am not bothered about for this part, right? Why? Because for there this denominator problem is not coming. Right? So what is my job? I will take this q by q matrix. Okay. So what are the basis for this? The basis is 1 0, 2 0, q 0, q plus 1 0, like that, right? So this part I am taking, I am diagonalizing it. So then I am moving to a new basis, which is, I am just writing it okay, let me write h1 tilde 1 1. So just for your convenience to remember. So this is h1 tilde 1 2 2, like that, h1 tilde qq. So this is the q by q block now diagonalized, right? And then rest is as usual. Rest I didn't do anything. So then you will have 1, 2, q, and then the same thing, q plus 1 0 and so on, right? So this is the job, to move from a basis 1 0 2 0 q 0 like that to 1 2 q plus 1 0. And how do I construct this basis? I construct it by diagonalizing this block. And constructing this block means it is equivalent to finding this a and k. Right? So this is the job, very simple job. Any matrix given, you just construct that, diagonalize it, and you are done. Now this is under the assumption, under the hope that after you do that, there is no further degeneracy. That is not guaranteed, and we will see that how will you deal with that. Okay, but you understood the outline, right? Okay, so let me write this in a flowchart form. It's an algorithm. It's that's the power of this whole perturbation theory and the whole quantum mechanics. Actually, it's everything boils down to a set of operations, linear algebra operation with matrix, vector, and differential equation. And it's quite remarkable that once that happens, everything is very simple. What is most difficult to understand are those basic things that a particle can be in two states at the same time. But once you accept those things, there is nothing difficult in this part. Right? It's just taking a matrix, diagonalizing it, adding, subtracting, that. Okay. So I want to do this problem where H naught is N naught. Okay. And E1 naught is Q fold degenerate. This is my starting point, and I want to solve this up to whatever order I can. Let's say first order for time being. So this is my starting point. Then what do? I construct a n. Your first step is construct the n in that q by q subbasis which diagonalize, and the construction is simple, it is just diagonalizing this, the submatrix okay. This is my second step, okay, which is basically it belongs to, it boils down to solving this equation. It's a secular equation. Okay, where A is basically this A n k. This solution will give you the A n k. Okay, so basically you solve this. This gives you a determinant equation because solving the eigenvalue means solving the determinant of this. This solution will give you a bunch of eigenvalues also, which is basically this solution of this non-degenerate levels. Okay, and these eigenvectors will give you the new non-degenerate basis. So this will give you the non-degenerate first order eigenvalue, and this is still zeroth order, by the way. This is still zeroth order because we know that when you solve a equation, this perturbation theory, for eigenvalues in a particular order, you get the eigenvectors in one less order, right? So this is still zeroth order, but this is the right basis. This is that right basis where you fall back when your epsilon goes to 0. Okay, so this basis is given by 1, 2, 2, q, and q plus 1, 0, and so on. Okay, this is the solution. So this is what you have to do, and solving this equation is very simple. This is nothing but construction of this matrix. This is construction of this H1 1 minus E11, H12, H13, and so on, right? H1, let me, yeah, 1, H122 minus E12, and so on, right? This matrix you just have to construct. And this is very simple because, for example, you are doing particle in a box, right? Particle in a square well. We know there are degeneracy in this problem. So all you have to calculate, let's say you have some perturbation, some potential you have added here, right? So you have to take this potential and calculate this. There are two quantum numbers, so one is nx, another is ny. Psi nx, ny. So this is what you have to do to leave the degeneracy. Now this problem has a little bit of other issues because here the degeneracy is not just in the ground state. In fact, ground state is not the degenerate one. All other states are degenerate. So, but idea is same. Wherever it is, you see degeneracy, you have to do this. You have to calculate this for that submatrix, and you have to calculate this accordingly. We'll do those examples. Okay, but the idea is clear, right? Online audience, did you get the idea of degenerate perturbation theory? What you have to do and why you have to do that? Any response? Anyone there?
Yes, sir, it's clear.
Is clear?
Yes, sir.
Okay. So now I will give an outline of what we'll do next. Everything I said so far is for ground state. Okay. Now we have to do a little more work and see what can I do if it is in excited in some random state in the middle of the spectrum, which is the case in most problems. It's a very simple idea, but it becomes a little cumbersome when I actually do this. Okay, so let's generalize it. So generalize means I have some levels, and this particular level in the middle is q-fold degenerate. Okay, so let's say this is some level m naught of eigenvalue em naught, and they have this q-fold degeneracy, which gets lifted because of the perturbation, which is what I assume. Okay, so your actual problem is h naught m naught, em naught m naught. These levels are q-fold degenerate. Okay. Now I want to solve the full problem, which I call EL. And when the epsilon goes to 0, so where h is some h naught plus h1, when the epsilon is taken to 0, then this thing should fall back and h epsilon goes to 0, that means h naught basically. Then I expect this to become some L naught, L naught, L naught. Now what do I want? I want the EL naught. Of course, EL naught will be equal to EM naught, but there is no guarantee that L naught will become M naught, right? Because it's an arbitrary linear combination. So I want to ensure that first, that I want to choose my M naught such that it always come back to that. Okay. Okay, even though they span the same degenerate subspace, and of course the usual problem. Okay. So the usual problem is this object. The usual problem is this object is ill-defined. We have created this object with so much care that En naught minus H naught is ill-defined, right? Because this acting on this phi n will give me 0 in many cases, in all these cases. Right? Okay. So when I act the phi n, this for this n space, it will give me 0. Okay. So now let's see how do I fix these issues. Fix these two issues. So the first job, okay. So I want to construct a combination of L naught, okay, which I am belonging to D. D is this subspace. So this subspace I call it the D space. I want a construction of this. So what did I do? I just basically used resolution of identity. So M naught, L naught. I expanded this. Okay. And I want this, want to construct this particular L naught, which I consider as my L naught. Right? Instead of that M naught, I will take that L naught, which are equivalent because they are linear combination, and that will be my starting point, such that when I epsilon tends to 0, this L goes to L naught. Right? And for the full problem, I took this to be L. So HL, EL, ELL. Okay, so now I will define two operators, two projection operators. One is Q naught, whose job is to project into this subspace. Another is P naught, which is the other rest of the subspace. So Q naught is nothing but M naught, and P naught is 1 minus Q naught. Okay. Just to separate these two spaces. Okay. So now I will use these two subspaces and do some algebra. Okay. So notice two more things. They are projection operator. So they satisfy this, that P naught square is P naught, Q naught square is Q naught, P naught Q naught, Q naught P naught is 0, and P naught plus Q naught is 1. Right? These things will always happen. We can know it physically and we can also test it, because P naught squared and P naught, what is the job of P naught? P naught's job is to project it into one space, right? Then square means what? You project it again. Now once it's already projected, what happens if you project it again? You get the same thing, right? So P naught square must be equal to P naught, and how to prove they are same? Just expand this, just use this expansion. Same for Q naught square, and P naught Q naught will also always be 0, because P naught is already projected into one space. Then if you use the projection operator on that space, it will give you 0, because there are two defined spaces. Right? So P naught is basically, if you want, you can call P naught is this degenerate subspace. This I call as Q naught, and the rest is P naught. Right? So whatever is projected here cannot be projected there, and their total is the full thing. Right? This is just physical picture, and you can also prove it mathematically. Okay. So now I am going to use these two equations and rewrite everything in terms of these two. Okay, I am thinking whether I should proceed from here. I will not, because there is a bit of algebra. So I will stop here, and I want you to, I will give you the notes, so look it up such that the next class becomes slightly easy. There is not much point in going deep into this. And internalize properly this method I told you about. How do you schematically, the schematic idea that why you need to deal with that way, the degenerate subspace, and how do you do it, how you actually operationally calculate the first order energy correction and 0th order state correction, right? 0th order correct states, not correction, 0th order correct states, right? So make sure you understand that. That is the informal solution. That is what you need to solve almost all the problems. And here I am showing you the formal way to get there, right? The formal way is using this projection operator and all that, right? And it's a very insightful calculation. It will help you to construct. Now you will see there is a very neat way. When I do this, why I am doing this formal way? The informal way is good enough, because the formal way will help you to get these formulas for any arbitrary order, not just first order. So that is what we will see. And there is a very simple. The structure will be very simple and very illuminating. Okay. So this is the what I'll do in next class, and meanwhile try to get used to that, and I will give you some problems also. I will give you actually my pre-recorded lectures on the problems. Then you can look at the problems and you get a feel of how this thing actually works. Okay. Okay, that's all for today. So this is something I am warning you that classes are going to be a little heavy in algebra from here. So you have to follow it in real time. Real time means by the next class you come physically, you should have an idea about all this. Yeah.
P naught there and P naught there to be orthogonal.
Just a sec.